Warning: serious injury or death may result from the use of the equipment and techniques described in this tape. It is not intended to be used as a sole source or replace field training by competent instructors, nor is it a substitute for experience. The equipment and techniques shown may or may not be appropriate for a given rescue situation. It is the strict responsibility of the user to obtain thorough and qualified instruction in any and all rescue equipment and techniques. This tape is provided with no liability to the authors, publishers, or distributors, expressed or implied, in the case of injury or death to the purchaser or viewer. Welcome to High Rope Tech, the video series. I'm Dr. Bill Ramsey, along with Kyle Eisenhart. All the volumes of High Rope Tech are designed as an aid to learning the fundamental principles and techniques of rope rescue. There are many areas other than fire departments and rescue squads where rope rescue competency is important.
That's right. Police tactical teams, municipal high-angle rescue teams, industrial confined space organizations, the military, all these groups, although they sound quite different, need to know the same fundamental principles of high-angle rescue.
And principles are important. All those teams may have their own preferences for equipment and techniques, but all those preferences must be based on sound principles. Throughout the High Rope Tech series, we hope to bring you those basic principles. This is Volume 1, Introduction to Rope Rescue. In this volume, we hope to preview all the other volumes of the High Rope Tech series by describing the equipment and techniques used in rope rescue. Before we talk about these equipment and techniques, though, one of the critical factors in all areas of rescue certainly has to be safety.
Absolutely. And safety is the primary concern at all rescue scenes. You need to be aware of how important it is to your personnel, how important it is to the victim, to everyone who's observing even what's going on. The incident commander has the ultimate responsibility for everyone's safety. The rescue sector commander, for example, is responsible for the rescue personnel. But they can't see everything. So every person on the scene has a responsibility for their own personal safety and for the safety of the victim. You know, many times that's overlooked.
Right.
And it's important to realize that at each scene, if you have personnel available, a separate designated safety officer in charge of the overall safety of the scene is important. If you don't have separate individuals for that, the rescue sector commander or the incident commander must assume that responsibility. That particular role has to be filled.
Other than this overall general scene safety, it's important to talk about personal protective equipment and how important the safety of the individual rescuer and the victim is.
We tend to think a lot about, is my rope strong enough? Is my rope long enough? Is my carabiner good enough? But we seem to sometimes overlook personal protection. Personal protection is absolutely important. If the rescuer ceases to be functional due to a failure of his personal equipment, it isn't going to do the patient any good. So you can't skimp on these types of equipment. First thing you need is a good, high-quality hard hat. Whether it has a front brim or not depends upon the application and the somewhat personal preference. The mountaineering type helmets have developed without the brim because of the necessity of seeing straight up for their next move. The other helmets have tended to develop with the brim for protection from the sun and objects falling into the eyes. So I think this is not clear-cut either way in general rope rescue as to which might be preferable, which configuration. But what is important is that the helmet provide good protection from the top, from the front, from the back, and from the sides. So you need a good quality helmet. That helmet needs to have a functional chin strap. We talk about protecting the rescuer from falling objects. It's been my experience and personal observation over many years in the field that I have seen as many hard hats fall off of rescuers' heads onto people below as I have seen other major objects dislodged. A falling helmet is a lethal weapon. Have a chin strap that works and use that chin strap. A helmet does you no good falling through the air. If we're going to work our way down from there, eye protection is absolutely critical. You should have face shields or safety glasses or goggles, whichever is apropos to the situation, whichever the personnel feel most comfortable with and the situation dictates. But eye protection is essential. As we move on down the body, we come to hand protection. Gloves are critical. You have to wear gloves that allow you to have some dexterity. People choose from the two extremes of gloves sometimes. You see them come out with a big, thick, huge, heavy pair of rappel gloves or whatever they want to call them that provide so much padding and protection from heat that you lose dexterity. So you can't lock your carabiners and you can't tie your knots. So gloves have to be a mix between providing protection, which is their primary function, and still retaining dexterity in the fingers so that you can perform the functions. We look at foot protection, ankle protection as we go on down the body. You need a boot that provides ankle protection and stability, but you need good traction. I personally feel that large boots such as firefighting boots are not a real good choice for rope rescue applications. Something more similar to a mountaineering boot or a rough terrain boot, something that a hunter might use to walk in the woods, are a good choice. I think the real heavy technical mountaineering boots, like the high altitude boots, like walking around with a board fastened to your foot, aren't a good choice for most rescue applications.
What about steel-toed boots? In some applications, that's going to be required, right?
Oh, absolutely. I think that steel-toed boots are rarely a negative thing. I can think of very few applications, and the only ones that come to mind at the moment are technical rock climbing applications where a steel-toed boot might not be beneficial.
What about general clothing attire? I know that a lot of times rescue teams find themselves in multiple uses. Perhaps maybe they're with a fire department, and so they may be going to fires as well. But if you're into a purely rope rescue situation, a lot of times the very heavy type bunker gear can actually be a hazard.
This is true. We spent a long time evolving clothing, you know. I'm a great believer in the layering concept. I think that rope rescue personnel in general, if they're going to do a non-rope rescue scenario, would be far better off to wear something such as a jumpsuit that does not have a large number of loose objects on it. I don't like to see loose belts flopping around, tabs on zippers, anything that can become entangled in the rope if you're being lowered or being raised or you're rappelling or ascending. But you don't want big, bulky, loose clothing. I think that if you need more heat protection or more cold protection, proper underwear layering, you know, silk or polypropylene next to the skin, wool or Thinsulate, something like that over top of that, and your jumpsuit. Wearing big jackets and things like that can be a real problem. They can become entangled in moving ropes and equipment. So yes, I agree with you. I wouldn't wear bunker gear, for example, as a broad term, a broad classification of large, bulky, loose clothing, unless I needed it for protection. If I needed it, that's what I would wear. I would never sacrifice my protection from a fire potential because I was concerned about becoming entangled.
Absolutely.
You've got to keep your priorities right.
Right.
All kinds of things happen in the real world. And that protection, that personal protective envelope, we talk about that a lot of time in the fire service, personal protective envelope. You have that same thing in rope rescue. It consists of your helmet, it consists of your eye protection, it consists of your hand protection, of your boots, of the suit of clothing that you're wearing. You have that same protective envelope, and it's absolutely important to never leave any piece of that envelope out.
Let's talk a little bit about the construction of rope in general, the types of rope, and what the basic rescuer needs to know about those types for general rescue.
Ropes are manufactured in a number of different ways. There are two basic types of rope construction. There's twisted and there's braided. The oldest type of rope that we are familiar with is twisted. Twisted ropes were made by the Egyptians 5,000 years ago, and undoubtedly by people before them. What they did was they used natural plants that had long fibers. They took these long fibers and twisted them together, just one around the other, until they got into a yarn. Exactly the same way that we see the use of the spinning wheel and those types of products to make yarn, they made rope yarn, so to speak, that same way from natural fibers. And they twisted them together into ever larger and larger bundles.
And of course, the most common examples that we think of in the rescue industry, of course, of twisted ropes were the old vegetable fiber manila type ropes, and also, I guess, gold line is an example, right, of a twisted rope.
Gold line is considered the classic example of the twisted nylon rope used for rescue.
There used to be a lot of concern expressed that with the stranded fiber ropes, you could open them up and look inside them, and there was some concern when the synthetic ropes, which are constructed differently, which we also want to touch on, that you couldn't look inside them because they were of what we call kern mantle construction.
Kern mantle construction is a term that we hear used widely in the United States, although it originated in Europe. It's basically a core, a kern, and a mantle or an outer sheath. Generally, these ropes are braided to some extent. The core may be braided, as in highly elastic ropes, for example. Sometimes the cores are braided. It may be highly twisted, or it may have very, very little twist. The core may be nearly parallel strands, but the jacket or the outer covering is always some sort of braided construction. It may be one over, one under type of braiding like a herringbone, or it may go two over, two under type of construction, which we tend to see on what we call braid-on-braid ropes, which is a braided inner rope with a braided outer sheath. The most common example of those would be large marine hawsers. Large marine lines tend to be braid-on-braid because it's a very elastic type of and very flexible type of construction. But the kern mantles themselves that we generally talk about in rescue have lower elasticity. They generally have fairly straight core bundles inside and very tightly braided outer sheath. The strands in a stranded rope, because they're twisted, eventually all of the fibers come to the surface. Whereas in a kern mantle rope, the core or major load-bearing portion of the rope never is exposed at the surface. It is always protected by this outer jacket. And that outer jacket provides protection from abrasion and protection from dirt particles.
Let's turn now to the materials used in rope construction. First, let's talk about natural fiber ropes.
The National Fire Protection Association, in their 1983 ruling, states that natural fiber ropes shall not be used for rescue purposes. And this means that people who are using these types of ropes really need to move to newer materials. They need to look at ropes either of nylons or polyesters primarily.
Synthetic, if you will, is the term.
Man-made fibers, exactly. And the reasons for that are numerous. The primary reason that we have gone away from natural fiber ropes is because they rot. They just sit there, and the natural humidity in the air causes a degradation of the fibers. And once these fibers begin to degrade, they lose their tensile strength. And once that occurs, it's an irreversible process. We look at polyester or nylon ropes, and after 7 or 8, even 10 years of careful storage, the tensile strength reduction is very minimal, a very small percentage. They also have better flexibility. There's a great deal of concern and a great deal of old data about the flexibility of ropes and sheave diameters, for example, as opposed to rope diameter. We see these large ratios, 20-to-1 type things. And the reason for that is because natural fibers are in very short lengths. They're little pieces, maybe 4 inches long, maybe 12 inches long, but they're still short. And a synthetic fiber that's used for rope, for all practical purposes, is the entire length of the cordage. The same fiber runs from one end to the other. So by flexing it, you don't have the ability, these little short pieces that are just overlapped, to be bent until they fall apart from each other. So the going away from natural fiber ropes to synthetic ropes has made rescue much safer by an orders of magnitude, as far as rope failures are concerned in the field.
Right. Obviously, there's different ropes for different tasks, but of the synthetic ones, what are the most common materials that the rescuers are going to be seeing out there, and what are the considerations for the use of each one of those?
Okay, by far the most common material is nylon. Nylon fibers happen to have that ideal balance that we're looking for. They have excellent tensile strength. They have good shock load absorbing capabilities. They are not heavy. They're fairly light in weight. Their strength to weight ratio approaches that of steel. So nylon is by far the most commonly used material. I've mentioned polyester because polyester is used particularly in Europe and some other parts of the world, not as much in the United States, for life support ropes. Polyester is also an excellent choice. It is heavier than nylon, strength to weight ratio wise, and it has less shock load absorbing capabilities. That may be a problem in some applications. Polyester has slightly better resistance to dilute acids, for example, than nylon.
So a hazardous material team might find a piece of polyester rope more useful than a piece of nylon rope.
They may in some cases. On the other hand, the nylon rope performs better in a basic environment.
Right.
So, you know, it's all part of your tools. It's all part of understanding what it is that you want to do. You need to know your application. You need to know your tools. It's just like, you know, you have a 9/16 box and open end wrench. Which end of it you're going to use depends on your application. It's the same way in rope. We have polypropylene ropes, for example, which are excellent for water applications. Polypropylene floats. Very nice. Your rope doesn't do you much good if it's laying on the bottom of the river
Right.
and you're trying to retrieve it across and it gets snagged on a log or a rock. It does, however, have less tensile strength and it has less heat resistance. So you wouldn't want to rappel on a polypropylene rope, whereas you could rappel on a nylon or a polyester rope without worrying about that heat buildup problem.
The most common example of polypropylene that might be familiar to rescuers in general use is, of course, the polypropylene ski tow ropes that are used in marine applications. A lot of those are polypropylene.
Yes.
And you'll notice that they float on the water, but a serious flaw, of course, with with those ropes is if they're left out for extended periods of time, they lose a lot of their strength with ultraviolet exposure and melt very easy, as you were pointing out.
Right, that's a good point. Ultraviolet exposure is a concern with any synthetic rope. It's tend to be ignored over the years with natural fiber ropes, but ultraviolet attacks natural fibers just as much as it attacks synthetic fibers. It so happens that the natural fibers usually rotted before the ultraviolet degradation took over, so we didn't think about it very much. It didn't last long enough for it to matter. But with nylon ropes and polyester ropes and polypropylene ropes, it's important that you not store them in the rear window of your car, for example. You want to keep them out of sunlight, and ultraviolet degradation is actually a major concern because they are so stable in every other way.
Right.
So we tend to lose track sometimes of what's truly important. It was a concern that stranded ropes could be sort of untwisted in your hand and looked inside of, but these kern mantle ropes, you can't see inside of them. And for many years there was great debate about whether that was a problem or not. What we have found over the years by literally looking, cutting apart and looking at hundreds and hundreds of used ropes, we have never seen in what we call a static or a dynamic kern mantle rope, and those are relative terms, of course,
right,
but generally used in the industry, the 1/1 tightly braided sheath ropes, let's say, regardless of their elasticity. We've never seen one of those in which there were dirt particles inside, eating away at the core, and the outside was not visibly damaged seriously. So our concern that these dirt particles would migrate into the rope and act like a hidden, eating away hiddenly, from historical data we have determined that's not a concern. The things that we don't want to have happen with ropes is we don't want to have any foreign material that might be on the outside of the rope to be physically forced into the core. We don't want it to be mashed in by walking on it. We don't want it to be, the sheath to be breached by sharp objects on the ground that the rope's laying on, and then by pressing on the top of the rope, you force them in. And we want to wash them. We'll keep them clean.
How do you recommend washing a rope?
The normal way we wash a synthetic rope, whether it be polypropylene, polyester, nylon, we put the rope in a container of warm water. Not hot water, but warm water. You use a mild soap. In the case of nylons and polyesters in particular, you want to make sure you do not use a bleach, chlorine bleach in particular, containing detergent. The chlorine molecules will react with the backbone of the polymer and will cause a failure, premature failure of the fibers. So you wash them in warm water. And again, this just needs to be warm enough to help the soaps and emulsifiers to carry away the dirt, because very few of them work well in really cold water. So warm waters, and then you rinse the rope thoroughly, and we tend to recommend the use of a liquid fabric softener in moderate amounts after the washing and the rinsing of the soap out is completed. And that fabric softener serves as a lubricant, actually. It doesn't soften, so to speak, but it actually puts some lubrication back on the fibers so that they may slip by each other more smoothly without dragging and tearing at each other.
Obviously, ropes get wet if you wash them that way. They get wet in the field. What's the appropriate way to dry a rope?
Drying ropes is really fairly straightforward. We try to make it difficult. The best way to dry a rope is to hang it in loose coils in a dark place that's fairly warm. You can have airflow directed over them, but you don't want to blow hot air over them.
So you've got it dry now, you're ready to put it back in service. What about storage? I know some mountaineering groups prefer to wrap their ropes in mountain coils, which certainly has appropriate benefit, obviously, if you're need to carry it over your shoulder or something. But in general, for rescue, what are some of the other ways we can store rope, or the ways, I guess, that we found most useful to store ropes?
The ropes are, you just make a blanket statement here, ropes are best stored in rope bags. We used to coil ropes and hang them in the compartments, and they looked so pretty. But when you went out in the field to use them, you had a giant snarl. So you put your rope in a rope bag, and you put it in the rope bag in a haphazard fashion. The objective is not to coil it in a neat little coil inside the rope bag. The objective is to just sort of flake it in there in layers.
Those of us who use rope bags could relate to that, because when you try to coil them in around, it comes out looking like a telephone cord.
Exactly. And the modern ropes, the static kern mantle, dynamic kern mantles, braid on braid, these ropes are made in what we call a zero torque construction. And what that basically means from a manufacturing point of view is there are as many turns to S as there are to Z, or left to right. In other words, you balance the number, the torque within the rope to go this way with the torque within the rope to go this way. So they cancel each other out, so the rope doesn't want to twist. And it's important that you store your rope properly, or you can destroy that very property. If you recoil it all up and you pull it out, it's just like an open-face spinning reel. You pull the line off over the end of the spool, it's got all that torque in it. So that's why you want to get that random
So just
pattern.
stuffing it in the bag is random, and it doesn't tangle when it comes out, and it does well. So that's good for storage, obviously. Just to recap for a minute, so far we've talked about the different types of construction that we see in ropes. We've talked a little bit how to care for those ropes and some of the basic characteristics of those ropes. But you mentioned before, and I think it's important to point out, the difference between what we call static ropes and dynamic ropes.
Dynamic versus static are terms that are relative terms, especially static. Dynamic isn't real relative, we all understand that. But the term static, as utilized in the rope industry, means a rope of relatively low elasticity. A rope that under a body weight of, say, 200 pounds, roughly 95 kilograms or so, would stretch less than 3% of its original length. So no, it isn't static in the sense that it is a concrete block, but it certainly is a term that people can relate to and understand.
Static meaning then low stretch.
Meaning low stretch, exactly.
And dynamic must then mean more stretch.
Exactly. The dynamic ropes that we generally refer to are ropes that their widest use is in mountaineering type applications. Specifically in those applications where an individual may fall an extended distance on a fairly short piece of rope. As an example, if you were to be on the balcony, the third floor balcony of a hotel, and your rope were secured at the third floor balcony, and you were to climb up to the fourth floor balcony, now you would be above your anchor point, and for some reason you were to lose your grip and fall, you could fall to the second floor balcony. So now you've fallen 20 feet, for example, on 10 feet of rope.
Right.
So you need what we would call a dynamic rope, a rope that has a lot of elasticity, so it can absorb a great deal of that energy so your body wouldn't have to. Whereas the static ropes, let's go back to the third floor balcony again. If you come out on the third floor balcony with a static rope, you would go down to the second floor balcony. And if you were to lose your grip, you might fall a couple of inches. But you're not going to fall 20 feet, you're going to fall 1/10 of 1 foot. So what we would call a static rope would be very good for that, because you wouldn't fall a long ways and maybe eventually hit something below you.
Right.
Also, static ropes are the ropes of choice for rappelling activities, because you don't want to be bouncing around when you want to stop, for hauling applications, because when you pull on the rope you want the load to move. For the vast majority of rescues, I mean, I don't know what kind of number I want to use, 95%, 99%, but it's up in that range. Static type ropes, low low stretch, low elasticity ropes are by far the most desirable. They come in a wide range of diameters, for example. Dynamic or high elasticity ropes are only made in fairly small diameters. They're made in diameters from 8 millimeters, for example, up to 11.5 millimeters, about the biggest you ever see. And that's a half an inch. And they are much lower in ultimate tensile strength than low elasticity or static type ropes. Dynamic ropes, by virtue of the fact the yarns have to have a great deal of elasticity, they are made from lower ultimate tensile strength yarns. They are designed to give. They are not designed to hold a huge load. The static ropes are designed to hold these heavy loads. They come in diameters 5/8 of an inch, for example, 16 millimeter. That's a big rope. And they're very, very strong. 5/8 ropes are used primarily for heavy hauling systems, where there might be a multi-person load, or for traverse lines, which the rope would be strung maybe horizontally across something and would be center loaded, so you need that extra strength. A commonly overlooked area, for example, where you need a 5/8 rope might be a slope, a fairly steep slope, maybe 40 degrees, where you would be carrying a litter with a patient in it, and there might be 4 people.
4 litter bearers.
Right, so now you've got 5 people on one rope that are being protected by one rope. While you don't have their full body weights, if they were to slip and fall and one person falls and knocks all of them down, all of a sudden you've got a big load on that rope. So the big rope is an advantage. The other thing is a lot of just hand over hand pulling is done on ropes in the real world of rescue.
Right.
And they're easier to grip. It's hard to pull on a 3/8 rope, but it's really easy to get a hold of a 5/8 rope. So just purely physical handling, there's advantages to big ropes.
Sure. We've been talking here in the last couple minutes a lot about rope strength with reference to sizes. We've mentioned a couple terms that are important. The term tensile strength. Sometimes we talk about a term known as safe working load. Let's go back and define or look at a couple of those terms. First, let's look at tensile strength, also sometimes called breaking strength.
The terms ultimate tensile strength or breaking strength are used interchangeably within the field. And they relate to that absolute ultimate load at which catastrophic failure occurs. Obviously, we never want to approach that in the field. There is no reason we should ever approach that in the field. The term safe working load is the only thing that's really important to the end user. And the safe working load is a very small percentage of the ultimate tensile strength. I have a diagram over here on the board that I think is extremely useful for us. This particular diagram is what we call a stress-strain curve. Stress is elongation or elasticity. Strain is a load, whether it be in kilograms, pounds, whatever you want to talk about it as. When you begin to pull on the rope, you start to pull on it, these little braids that run around and around begin to straighten out. And as they begin to straighten out, the rope elongates more rapidly for the load than just the fibers themselves would elongate if there was none of this mechanical let-out. Okay. So this mechanical let-out plus what we call initial modulus is this initial part of the curve from 0 to A. Now, when this mechanical let-out ceases to be a significant portion, this runs in a straight line to point B. Point B is the ultimate maximum safe working load of that piece of equipment, whether it be a rope, a carabiner, a pulley, a piece of webbing, a piece of chain, a piece of steel cable, it doesn't matter. Point B is the ultimate safe working load. Once you go past point B and proceed up this line until you eventually reach point C, which is the final ultimate failure, everything that occurs between point B and point C irreversibly damages that piece of equipment. It can never recover from any loading in this section. It's gone forever. So point B, which we refer to as the maximum safe working load, should never be exceeded. You need to realize that point B varies depending upon the material. If it is a synthetic material such as nylon, point B may be 10% of point C. In other words, if it's 1,000 pounds ultimate tensile strength, the safe working load may only be 100 pounds. On the other hand, if it's a piece of chain and the ultimate tensile strength is 1,000 pounds, we may have a 20% safe working load of that, so it's 200 pounds. So the thing that's most important is to realize that you should never exceed safe working load. Safe working load is established by regulatory agencies, and it is always a percentage of ultimate tensile strength. So as long as you never exceed safe working load, you don't have to worry about damaging your equipment.
Say we're dealing mainly today with usually half-inch kern mantle nylon ropes or 5/8 inch kern mantle nylon ropes. What's the general safe working load percentage?
The currently established ratio for fire service safety on rescue ropes is a 15-to-1 ratio. In other words, a 9,000 pound ultimate tensile strength rope has a safe working load of only 600 pounds. So anytime you exceed that 600 pound load on that rope, you're reaching into this area up here. So that rope is damaged beyond repair. It will never recover from that.
So we use 15-to-1. That's, I guess, what, NFPA
That's the National Fire
recommendation.
Protection
Now,
Association
obviously, that's
recommendation.
based on this stress-strain curve,
That's correct.
and probably even a little more generous, maybe.
Well, yes, it is, because there's ultimate safe working load, which I talked about as being point B, and then there's recommended safe working load. And the recommended safe working load, which is the number that the NFPA, for example, presents, is usually in the 80 to 90% of that.
I see.
So it's even more conservative.
So that 15-to-1 in general gives us very good safety margins.
Very good safety margin. And I think, again, while we're talking about safe working load, people need to realize that it is there to take care of reduction in rope strength or equipment strength due to a whole number of factors. Aging, abrasion, knot tying in ropes, for example. People look at a rope and they say, well, if I tie a bowline in it this particular diameter, I'm only going to have 80% of my ultimate tensile strength left. And they question, do I need to refigure safe working load again? And the answer is no, because safe working load is only figured one time. It's figured on the ultimate tensile strength of the new material.
So that takes into account how old the rope is, the knots that are tied in it, what wear it may have during its use, a bend around a small sheave pulley, a bend around a carabiner. All of that is taken into account when we talk about safe working load.
That's correct. That's absolutely correct. And a very important point to remember, safe working load, let me repeat it, is only calculated one time on the basis of brand new ultimate tensile strength of the product. Webbings come in a number of different colors, and they come in different constructions. There is flat webbing that looks like your car seat belt material. It's normally either nylon or polyester. There is flat, narrower webbing. There are tubular webbings in a number of different diameters. And externally, the tubular webbing and the flat webbing looks the same to the casual observer. But up close, the tubular webbing is actually a hollow tube. It's hollow inside. It can be opened up and things put through it. We tend, in general, to look at some of the thick, flat weave, solid weave webbings as being more abrasion resistant and stronger than the hollow or tubular webbings.
Why do we even need pieces of webbing? We have rope. It's a nylon material or a synthetic material. We can tie knots in it. We can use it to rig.
Good question. Webbing related to rope is the same as the box and opening and wrench again. They both fit 9/16, but one may do better in one application than another. For example, if you wanted to make a harness to go around your body somewhere, you would be much happier to have a 2 or 3 inch wide webbing around your body than you would a little narrow piece of rope around your body. The rope would tend to bite in and cut you, and where the webbing would obviously put the load over a wider area of your body and be more comfortable.
Many times we use webbing not only for making harnesses, obviously, but sometimes use webbing for slings. What are the advantages of using them in a sling situation? I notice that some of these even are already stitched.
Right. That's of course the biggest advantage of them is they tend to be easy to use. They can be stored in a very small area. Webbing is generally easier to transport in a small area than rope. Rope takes more volume. Webbings can be stitched into nice little loops in the end. The more modern rope construction methods, for example, the kern mantle, do not lend themselves well to splicing. So if you want to put a loop in the end of something, a short piece, for example, to wrap around a post or a pillar or something, a piece of webbing with loops on the end of it is just handier,
Right.
just easier to use.
Right.
So that's why we make slings in particular out of webbing. We have various methods of making webbing. In the old days, webbings were all made with what we called shuttle looms, which worked a lot like you see the Native Americans and other places in the world, you see them weaving rugs where they have a shuttle that runs back and forth to produce the webbing. Now there are more modern machines that are called needle looms, and they weave in a different fashion. There was concern for many years that the needle loom webbings were not going to hold up as well as the shuttle loom webbings. And some of the early needle loom webbings made 20 years ago didn't hold up as well. But the modern needle loom webbings work just as well as the shuttle loom webbings. The specifications throughout the world have changed for webbings, and needle loom webbings are now used just as widely as shuttle loom webbings. So that's not really a big concern whether your webbing is needle or shuttle loom as much as the material from which it's made, the specification of which it's made, and for the end user, probably the reputation of the manufacturer and supplier might be the easiest way to determine if they want to purchase a particular product. During World War II, the military decided they needed some ways of attaching things together in the field. So little oval steel links were developed. They looked like a big chain link that one side opened up, was spring-loaded, had a little gate in it, and they were called carabiners. They actually existed before World War II, but their widespread introduction to the United States was because of military activities in the Second World War by our Special Forces personnel. And carabiners or snap links, as we generally see them today, are made from different materials, primarily aluminums and steel. They come in what we call locking, and non-locking varieties. They are in many shapes, and their description basically refers to the overall shape of the carabiner. We have oval carabiners. We have D-shaped carabiners. We have pear-shaped carabiners. We have modified D carabiners. We have twisted carabiners. Steel carabiners in general versus aluminum carabiners in general, we find that strength to weight ratio on aluminum, as we all know, is very high. So you can make a strong carabiner from aluminum, and there are many very strong aluminum carabiners manufactured, and they're light in weight. But in the rough and tumble world of rescue, they don't seem to hold up as well as steel. They tend to get scratched and nicked. The gates tend to get dinged. They don't operate quite as smoothly over the long haul. Also, the primary market for aluminum carabiners is the recreational market. So they tend to be driven towards smaller, lighter weight configurations. Whereas the rescue market is driven in the other direction. It is driven upscale toward large, heavy, extremely strong attachment devices. So the steel carabiners in general use are larger and stronger than the aluminum carabiners in general use today.
Steel versus aluminum, I think we've covered. How about oval versus D, or the different sizes and shapes of carabiners?
The oval carabiner was the earliest and original configuration. Then what happened was the scientists became involved and the engineers, and they said, you know, this oval carabiner, both the backbone and the gate are loaded equally, so it's weak. If I were to bend it into a more of a D shape and make the backbone straight and bend it sharply and open the gate over on the other side, I could make a stronger configuration. So the D shape and the modified D shapes were born to get higher strength, not to get more utility necessarily, but just higher strength to weight ratio. The pear shapes, which are just ovals that are bigger on one end than the other, were primarily designed so large objects could be hooked onto by the carabiners.
For example, like on a ladder or a pipe, something of that regard.
Exactly. They just need more gate opening. That's the sole driving force behind that. And that has been carried even further today with carabiners that have gates that open at an angle to the backbone. So the gate swings past the back of the carabiner and allows it to open even further.
What about special application of carabiners? You talked about a twisted carabiner or a twist link carabiner.
Right. We found that sometimes a planar carabiner, which is what they normally are, we had to hook two of them together so we could change direction. And then the thing got longer and it got sloppier. So special carabiners such as the twisted variety have been developed so that rigging can be reoriented in a short distance. The National Fire Protection Association wrote a standard in covering rope rescue equipment, and within that standard, standard 1983, they addressed carabiners, and they say that within the standard that no carabiner can be used for rescue of the non-locking variety. So locking carabiners are the only ones approved by that particular regulatory agency for rescue. The figure 8 is a simple device. It has no moving parts, and for that reason it has been widely used. It is a fixed friction type device, meaning that the friction cannot be changed dramatically once the device has been applied to the rope. Normally they are used with little ears attached to the top of it. It's called a winged 8 or an eared 8.
What about other friction devices?
Well, certainly the most flexible friction type devices are variable friction devices, of which the most common ones are racks. Racks come in two basic configurations, open frame and closed frame. An open frame rack is the common rack used in recreational rappelling, and the closed frame racks are widely used for lowering heavy loads such as litters with multiple personnel. The real beauty of variable friction devices is that once the rope has been applied to the device and activity begun, the friction applied to the rope by the device can be varied as conditions warrant. Ascending devices or rope grabbing devices, they come in two broad categories, closed frame or shell and open frame or open shell, meaning that in a closed frame, a closed shell type ascender, the rope is completely enclosed and it is not easy for the rope to be removed from the device. Whereas in an open shell type device, the rope is not totally enclosed by the shell. Common examples of closed shell type devices would be Gibbs ascenders. In this country, there are certainly similar devices made throughout the world. The most common open frame type, open shell type devices are Jumar brand, CMI brand, Petzl brand, Clog. They have their greatest utility because they're quick and easy to attach and remove from the rope. That can be a big advantage as a personal safety or a personal ascending type device. But in the heavier loads that might be applied to the device, such as in a hauling system for a litter that may have 2 or 3 people in it, those devices are weaker and generally have more damaging effect on the rope than closed shell type devices. And while we're talking about rope grabs, I think it's important to realize that if there is a rope grab in the system, in general, that rope grab rope interface is the weakest link in that whole system. Pulleys are one of the most important tools you'll ever use in rope rescue evolutions and applications. Pulleys are used for so many things. Pulleys are used to traverse loads along relatively horizontal ropes. They're used as change of direction. They're used for mechanical advantage. They're used, and they're special pulleys. They're real wide pulleys that you use to pass knots on ropes. There are narrow pulleys that are used with cables. The groove shape for a cable pulley and a rope pulley is different. What the side plates are manufactured from, the clearances in them, all these things are very important to selection and proper application of a pulley. And another area about pulleys that is widely discussed is the importance of the sheave diameter to the rope diameter. Fortunately, with the modern synthetic ropes such as nylon, polyester, polypropylene, they can use a much smaller diameter sheave as a ratio of the rope diameter without having those problems, again, because of the continuous fiber that's used in the manufacture of the ropes. There's a lot of places this rope is going to be subjected to a tighter bend than around this pulley. So it's probably not going to fail at the pulley sheave rope interface.
That brings up then, where is the weak point in the pulley itself?
And of course, it varies from pulley to pulley and depends on how the pulley is designed and what it's manufactured of. But in general, the failure is by shear in the small amount of metal between the hole that the attachment point goes through and the end of the pulley.
Right.
In other
So
words,
the metal pulley pulls apart there.
Tears right through the top end attachment point of the pulley. The classic multi-sheave block and tackle systems are very useful for certain applications. The modern multi-sheave pulleys use exactly the same technology as the single sheave pulleys. The same types of bushing bearing surfaces apply, the same types of sheave diameters, ratios, sheave grooving, all those things, the same materials of construction. They just put, as you said, more sheaves on the same axle so they get as many as they need. Harnesses have so many different designs. So every organization, every regulatory agency, it seems, wants to come up with their little way of describing these things. Most of them are slowly coming into classes. Class 1, Class 2, Class 3 are commonly heard. Class 1 belts are used primarily for positioning, to prevent someone from getting into a position in which they could fall. Then the next class up would be like a Class 2, which is an actual seat harness in which there is not only the waist encircling band, but there is some other support for the lower extremities in the form of either loops that encircle the legs or a strap that runs beneath the buttocks to support the body that way. And these harnesses are used primarily for rappelling or lowering. So this leads us to the third class, which is the one-piece or Class 3 full-body harnesses. These harnesses were originally designed to provide fall protection. You see a lot of them around. They've got this big ring in the back, right between the shoulder blades. And that is the fall protection attachment point. And those harnesses are designed, if you do get to the edge and fall over, to catch you. Another variation of that harness is the full-body rappel harness, which is basically a seat harness and a chest harness that are attached together and designed for rappelling with a built-in belay line at the top. We want to emphasize, again, the critical necessity of having competent instructors, practice, training, and an understanding of all of the techniques and equipment that you are using when you go into the field.
For more details on all these topics discussed in Volume 1, join us in these volumes of the High Rope Tech series.